Cool, thank you. I just need a second to set up my screen sharing. Sorry, I've been really having trouble with my screen sharing recently.
Oh, really? I think everybody's been having these computer issues. Here it is. I see it.
Oh, can you see my presentation now?
Yep, I can.
Okay, do you see the slides now or the presenter view?
I see the what is astrophysics slide.
I have an astrophysics meeting.
Hi. Yes.
I'm
Perfect.
so happy.
Yes, that's the slide. Should we give a minute more for people to come in, or shall I start?
You can start. I'll just mute if they haven't muted. Usually they mute it. It's on mute when they come in, but I'll mute them for you. Okay, so go ahead. Okay.
Awesome, thank you. So hi everyone, my name is Momchil Molnar. I am a graduate student in CU Boulder, University of Colorado Boulder. And I'm also doing my PhD or my further graduate studies in the National Solar Observatory. I'm still a doctorate, a PhD to be, so I'm trying to be a scientist yet, but I would love to talk to you about today what astrophysics is and what the whole field is about. And I want to start with the last thing I want to show today as well, and that's the first picture of a black hole that was ever made, and we just got it very recently. And that donut-shaped thing is the black hole, and the black center in it is the actual black hole, and the donut around it is the gas that's falling in, and it's so hot that it's glowing red. It's very, very hot. It's like thousands to millions degrees hot. So and it's pretty amazing how we're able to observe that. And I'm going to tell more about it in a minute. But I would like to have this more as a discussion, not just me asking questions. Talking my monologue all the time. So if you have any questions at any point, please unmute yourself and ask them. And I'm more than happy to be interrupted all the time, because I think that's more enjoyable for everybody. So yeah, just to introduce myself. I'm originally from Bulgaria. Bulgaria is this small country that's on the left map over here is circled in Europe. I came to the States for my bachelor's degree, and after I finished my bachelor's of science, I went to school in University of Colorado Boulder to do my PhD, and I'm currently in Colorado. And Colorado is that green state in the right-hand map. And I've been doing my PhD for 5 years now, and I have one more year. So it's a lengthy process to become a scientist or to become a PhD. And I'm still learning a lot every day. So if you ask me a question, I might not know the answer as well. So yeah, scientists don't know everything. That's an important thing to keep in mind. What I study on my daily basis as an astrophysicist, I study the sun. Like that's our favorite star that we can see every day on the sky. And this is a illustration of the solar system, how it looks like. And the sun is in the center because the sun is the center of the solar system. Everything in the solar system goes around the sun. And it's my favorite star as well, because I'm studying it every day. And what I do on a daily basis is we use telescopes like this. This is the Inouye Solar Telescope, the telescope on Hawaii, that we use to look at the sun. And it's actually, it's so big. Its main mirror that collects light is 4 meters. It's 4 meters in diameter. That's almost 14 feet. And you can imagine if you have like a small magnifying lens that you used to burn stuff when you were little. Like how hot it becomes when you have like a small magnifying lens. But then imagine if this magnifying lens was 14 feet large. That's like really a lot of heat. So that's why what you're seeing behind the telescope is actually an ice factory. Like it's the well-hidden secret that actually most of the energy that we're using for this telescope. But one of the few cool results that just came out from this telescope are those images of its surface. This is the bubbling surface of the sun that you can see. It's called granulation. Each one of those small granules that you can see here is as big as Texas. And this is the best image that has been produced. And that was from this telescope. And what this tells us is how the sun actually the sun creates heat and heats the Earth. And that's very important. And that's why we study this. Another really cool picture that came out of this telescope recently is this picture of a sunspot. Sunspots are concentrations of magnetic field. So it's like a very strong magnet that was buried under the surface of the sun. And that's how we see them. And this is also the image of a sunspot with the highest resolution ever made. So that's something pretty cool from my day-to-day job as a scientist. We get to see things in unexplored detail before. So it's a little bit like in the crime, like the police crime movies, where they zoom in on the faces of people from photos that are very blurry. That's what we do with those very big telescopes. We zoom in very, very closely on the objects in the sky. But I'm not going to talk about today about the sun, since I did this last time and I talked a lot about the sun. Today I'm going to try to talk about more what astronomy and astrophysics is about. What do we study and why do we study it? And in order to give perspective of what we do as an astrophysicist, let's start with the solar system. This is our local neighborhood where the sun is in the center. You can see the Earth is orbiting around it, and there are the 8 other planets. But there's many other dwellers around there. There's the comets and asteroids. But the solar system is not unique. There's actually a lot more solar systems out there. And actually, there's a bunch more of solar systems that create our local galaxy called the Milky Way. And over here, you see artist's rendition of how our galaxy looks like. And the sun in the solar system in this case would be a speck on this illustration that you actually won't be able to see since it's so small. But astrophysics studies beside our solar system. It studies large objects like the galaxies as well. And like our galaxy, that's called the Milky Way, you can actually see it with your naked eye, which is one of the coolest things that you can see on the night sky, is that you can actually go out when it's very dark outside and look up, and you're going to see this very, very faint and large like spill of milk. It does look like if somebody spilled milk on the sky. It's like endless number of stars that cross the whole sky. And if you have a chance to see it, it's a very awe-inspiring scene, and I really recommend like sometimes trying to get out somewhere very dark to see it. So we could see our galaxy with our bare eye. But actually, what astrophysics also is trying to understand, beside like our galaxy, is how all galaxies in the universe came around, and how the universe started from the Big Bang. Like in astrophysics, we believe that the universe started with a very big explosion called the Big Bang, and then the universe started being as it is, and then it started expanding and cooling down up to the point that we are now living in a very cold universe. Like in this case, all the way to the right of this in this graph, we live in a universe which is very dark. It has a lot of it has us. It has at least one species of life, but it has galaxies, it has stars, but it's mostly empty and very dark and cold. So astrophysics is in a way also studying the history of the universe beside like its composition. So just because light travels with finite speed. So when you look at something that's very far away, you actually see how this object looked in the past. For example, the sun is about 100 million miles away from Earth. So the light takes about 8 minutes to go from the sun to Earth. So when you look up at the sun, what you're seeing actually is how the sun looks like 8 minutes ago. Well, imagine if you're trying to look at a very far away star or a galaxy. Well, their light takes hundreds of thousands or millions of years to come to us, so we see them in their past. And if we look even farther away, we see even farther away in the past of the universe. So you can think of astrophysics as a way of an archaeology of our universe, just because we see so far back in the past of it. But I would like to come back to our solar system and try to go out in scales, to start from the smallest things we study to give you an idea of what we do and how this whole idea of archaeology of the universe works. So this is a very simple schematic of the solar system. The solar system consists of the sun in the center. Then there's the 4 rocky planets that orbit around it. The closest one is Mercury, then it's Venus, then it's Earth, and then it's Mars. Mars has been the goal of humanity to colonize another planet and maybe create a second home for our civilization. And right after Mars, there's the asteroid belt. Asteroid belts are just a lot of very big chunks of rocks that were never able to get together and create a planet. They're just very large. We call them asteroids. Those big chunks of rocks. So those asteroids create a belt just outside of Mars, of the orbit of Mars. Then after the asteroid belt, then there's the 4 gas planets: Jupiter, Saturn, Uranus, and Neptune. Those planets are very, very big. And I'm going to go to the next slide. Like for scale, the next 4 planets are really, really big. Like you can see how smaller the inner 4 planets compared to Jupiter, Saturn, and Uranus and Neptune. And they're very big, but actually they're made out of gas. So if you can take Saturn and put it in Earth's ocean, it's going to float like a floaty because it's so light. It's made mostly out of hydrogen. So even though these planets are very large, they're not very dense. And we don't fully understand why do we have such strong separation between rocky planets being close to the star and gas planets being cast away so far away out. That's a thing we're trying to understand, because we've seen around other stars that actually we are seeing the orders reversed. We've seen the gas planets very close to the star, and then the rocky planets being kind of far away. So that's very interesting. That's a thing that we're trying to study as well. I want to briefly mention about Mars, and this, especially in since I think it's very prominent in modern culture, that everybody is trying to sell it as our future Earth, as Earth 2. But even though we've sent so many missions, and this is like a small chart of all those missions going to Mars, and there's been, I think, 40 something, including 5 or now 6 landers on it, we still haven't found any signs of life on it, which is kind of scary, because we might be the only type of life in the solar system. But also we haven't found any traces of atmosphere on it, or like frozen atmosphere, which might mean we might be never able to terraform, which means transform Mars to look like Earth, just because we don't have enough gases on it to create an atmosphere to protect us from space. So, but still, Mars is very interesting for many reasons, and it's a central piece of central study object of many astrophysicists, just because it might have harbored life in the past, and it's one of the closest planets we know to Earth. And the recent Perseverance rover that landed this year on Mars has been extremely exciting for this. That's a picture of the Perseverance rover with all of its scientific experiments and cameras, with all of their acronyms. And each one of those acronyms, or like the names of those instruments, actually stands for some very complicated scientific name. But since scientists want to be able to name their instruments with pronounceable words, they pick up those names. For example, a pixel stands for the X-ray spectrometer, which is something, it's a device that can tell you what rocks are made out of, for example. Or my favorite, the coolest thing that this rover did was the MOXIE experiment that you see down there, that actually produces oxygen from Martian carbon dioxide from the atmosphere of Mars. And it recently worked out, which is amazing, because this is the first time where we've been able to create oxygen from carbon dioxide on another planet. And this is like one of the stepping stones if we want to be able to go to another planet. Like if a human being is going to go to Mars, this was a very crucial step, and we achieved it literally a few weeks ago, which was unbelievable. And I think is like super exhilarating for the future of space exploration, because we're getting closer and closer to actually sending humans on Mars. And
I listened to that.
I saw that.
I'm sorry, Momchil. I read that yesterday, as a matter of fact. So you're saying that they're testing out how to put oxygen on different planets and how the reaction would be. I never finished reading, or maybe they didn't have it on there, but what was the reaction to oxygen being released on the planet?
Oh, that's a very good question. I had to dig pretty deep to understand it either. So I think what they do is Earth's atmosphere is mostly made out of nitrogen and oxygen, but Martian atmosphere is way thinner. You can think of the Martian atmosphere as if you've climbed on Everest and then you went even higher. It's very thin, but it's made mostly out of carbon dioxide. So that's that molecule carbon dioxide has one carbon atom and two oxygen atoms. And what we breathe, what keeps us alive are the oxygen atoms. You want to have free oxygen to breathe. So what this instrument did was it sucked out carbon dioxide from the Martian atmosphere, which is not very complicated because it's mostly carbon dioxide. It sucked it out and then it heated it so much that actually this molecule broke, and the carbon and the carbon atom get detached. The carbon atom got kicked out, and you get left out with free oxygen. And that's what they did in that case. And that's the first time that this has been done on another planet. I hope this answers your question. Yes,
it did. Thank you very much.
Yeah, and I think this is the coolest thing by far, because this was one of the limiting factors of space exploration, is being able to create oxygen, because we use oxygen for supplying breathing air for us, but also we use it for our rockets. If we want to have a rocket to work, you have fuel and you have oxygen at the same time, and you burn the two. So you need a lot of oxygen also to propel our rockets. And we're able to make that right now. So that's really, really exciting. Really exciting news. Yeah, but thanks for the question. That was a really good question. Yeah.
Have scientists found more gas planets than rocky planets in other stars' Goldilocks zone?
Oh, I'm gonna get to this in a second. That's a great question. Yeah, but yes, they have found more gas giants. Yes, but I'm just gonna get back to this in like 5 slides, if that's okay. I'm gonna answer it in great detail. Okay, and one of the coolest things that also happened was we flew for the first time a helicopter on Mars, and it's not the best video since it's coming all the way from Mars, but you can see that this small guy over here, it's actually a small drone that flew by itself on Mars the other day. It's literally like all those things that I'm showing you like happened in the last few weeks with the Perseverance rover. So the Perseverance rover had this small helicopter, or you might want to call it drone. This was called Ingenuity, and it flew by itself on Mars, which is pretty amazing. Like we had a robot sent all the way from Earth to Mars, and then this drone just flew around by itself. And I'm going to replay the video again. And this is a very major step forward, because if we can send drones to other planets, they can cover significantly greater distances and fly very far away and explore significantly more ground than our rovers. Because when you fly around, it's way easier to fly over a rock than crawl over a rock. It's like, you can imagine if like driving your car off-roading, it would be way easier to fly over the off-roading part with a helicopter. So that's also super exciting, and we're waiting on the data coming from this Ingenuity rover. But yeah, there's like a lot of interesting stuff happening on Mars right now, since there's so much interest of sending people there. Another really interesting mission that I'm just going to brief to is like the Cassini-Huygens mission that was sent to Mars, that sent a very amazing images of Saturn. And yeah, we went to like the gas giants as well. And but it's very hard. Sending a probe, like sending a satellite to the gas giants, costs a lot more money than sending a probe to Mars. So that's why there's been only a handful of those. But astrophysicists also try to understand those very large planets, and if they can harbor life in one of their many moons, because those gas giants, they have up to 50 to 100 from 50 to 100 moons each, and each one of them is actually protected is actually protected inside the extended magnetospheres, or you can think of it as the magnetic atmosphere of those large planets. So they might be harboring life as well. And I'm not going. The one thing I actually really want to talk about, since it's very common in popular culture to talk about, is like about asteroids, comets, meteorites, and bolides and meteors. What's the big difference between all of those things? So as I mentioned earlier, there are the 8 planets, but there's like a lot of other smaller space debris. You can think of them as just space gravel, like space gravel ranging from like very, very small specks of dust going all the way to rocks as big as 50 to 100 miles across. So they're very large, right? You can't call them like space gravel. But they're also very significant part of the solar system, and we have to study them. As because you might have seen one of those apocalyptic movies where one of them just falls and hits Earth and creates a global havoc. But actually, there is in place a global network for monitoring them, and I think we're in pretty good spot. I don't think anything is going to hit Earth anytime soon. But just to give you a short intro, like to the zoo of this type of object, the biggest pieces of rocks, they're actually made out of either proper rocks or metals, and they're called asteroids. They create the asteroid belt, and actually we're pretty interested in them because some of them are made out of pure metals. For example, there's some ones which are made out of nickel, which is a pretty expensive metal. So if you can go and mine one of those asteroids, you can make a lot of money. So a lot of people are interested in them. Also, there's like these really big pieces of ice, and when I say ice, it's part water, part methane, which is organic gas. And those things, when they freeze together, they make these huge snowballs that are could be a few miles across, and they're called comets. They're also just flying around. There's a lot of them in the outer solar system, like beyond the asteroid belt. And when they come close to the sun, actually they melt like a snowball will melt if you put it close to a fire. They melt and they leave those very beautiful tails behind them that we were able to see recently. There was one right at the beginning of the pandemic. I don't remember its name, but just a cool fact is that when there was the Black Plague, like the Black Death, the plague of the 1493, I think in Europe, they also hit a comet at the beginning of it. So people were trying to make some parallels between this pandemic and the Black Death in Europe a few 600 years ago. But that's a different topic. Okay, so if you have a little bit of a space dust that hits Earth's atmosphere, it actually burns in a very magnificent display. It's called a meteor. It's called a meteor, and they usually burn in the atmosphere. And actually, there's like thousands of them all around the globe all the time. And some of the time, there's more of them coming in. And those are called meteor showers. For example, there's one right now called the Lyrids, which is because all of the meteors seem to be coming from the constellation of Lyra, like the musical instrument. In a case that a meteor makes it through the atmosphere and hits the ground, it's called a meteorite. So it's the same exact thing. It just made it through the atmosphere and hit the ground, and it might have created a crater. And the one thing that decides if a meteor is going to become a meteorite is how big is it. If you're big enough, you're going to be able to go through the atmosphere. And there's like I think it depends how big they are, but you got to be at least a few centimeters to a meteor to be able to get all the way through the Earth's atmosphere, because it's pretty thick. It's pretty hard. And if you see a really, really bright meteor in the sky, it's called either a bolide or a fireball. And there's different definitions of them, but if you hear in the popular media fireball or a bolide, they mean it's like a very bright meteor was seen in the sky, and they might have created a meteorite that you can go and hunt after. And actually, there are people who get their livelihood from finding meteorites on the South Pole. And yeah, I heard it's pretty fun because you have to fly a helicopter over like the wide vastness of the ice for a while to find one, and they're really expensive because they're very precious for scientific purposes, because actually this all this junk, all the asteroids, meteorites, and comets are actually leftovers from when the solar system was made. And this is like a time capsule from how the solar system looked like 5 billion years ago. So again, astrophysics here is like an archaeology a bit, because we're studying the past and the origins of the solar system. Sorry. And actually, one mission that's coming out of Boulder on Boulder, Colorado, where I live in. It's coming from the Southwest Research Institute. It's called Psyche, and it's going to the asteroid called Psyche that kind of looks like this. Like it's actually, people think it's made mostly out of metal, like pure metal, maybe something like nickel and some other metals in it. So it's extremely dense, and it's extremely dense, and it's very dark. And people are very interested if we can go and mine it. And actually, we're able to send spacecraft to go and orbit around them and send pictures back from it. And that's happening in 2026. So yeah, in 2026, check this mission out. I think it's going to be very interesting because we've never seen an asteroid like this before from very close. Everything that we've seen before of asteroids like this was like one bright speck on our in our images. So that would be pretty exciting mission about it as well. But how as you alluded, there are a lot more solar system out there beside our own, and all of them have a central star and they have planets around. And recent work has been really concentrating on exploring those and trying to understand if each star has a planet, for example, and if there are that many planets, is there any life out there? Which I think is the biggest question we're trying to answer. And I think we've learned like significant amount, like this whole field of studying stars and their planets has been literally opened in the last 20 years. And the first major mission that found like hundreds and hundreds of planets around most of the stars looked around was Kepler. It was a mission that was it was a satellite that was, I think, a little bit smaller than a school bus, that was sent kind of far away from Earth to look at only one region of the sky. And it looked at the stars if there's gonna be a planet going in front of them and making the star a bit dimmer. And it did this for like, I think about 10 years. And it found that almost every star on the sky has a planet around it, which is a very large change in our understanding from a few years ago, when we didn't know that there was like a single planet. Like the first planet was discovered in 1991. And right now we believe there is a star around each planet, which is a very big change of mind for the community. And getting back to your question, yes, since when you have since most of the stars that we're finding on the sky is by seeing how much do they, how much of the light of the whole star is being blocked when those planets go in front of it. So actually, astronomers nowadays find mostly very large planets because they block more of the incoming light from their star. So actually, what we're finding most of the time is gas planets. And here's an artist's illustration of how those planets, how an artist thinks those planets look like. And most of them are gas giants. And you asked a really great question, like, do we find mostly planets like this? And the question is yes, we're finding mostly planets that are very large around our stars. But this is just because we're not sensitive enough to see smaller planets. This doesn't mean that smaller planets are not there. So we do think that there's plenty of smaller planets out there, but we just can't see them. And I think we will be able to pinpoint the smaller planets way better in the near future with a few telescopes that are coming online. One that's really exciting is the so-called Extremely Large Telescope, or the ELT, which has a 90-foot mirror. Like the mirror of this telescope is 90 feet. It's insane. It's 30 meters. It's like, they always give a comparison with a football field, but I really don't know how big a football field is. But I think it's like a half of a football field. I would love if somebody chimes in. I'm European, so I don't know football too well. But yeah, either way, this thing is going to be huge. It's like 30-meter mirror that's going to be pointing at one star, and it's going to collect a lot of light. So first, it will be able to really start looking for smaller planets, but also we're going to be able to start looking for oxygen and other organic gases in the atmospheres of other stars. And what this means is that when we're breathing in and out, we need oxygen and we exhale carbon dioxide. But also there's plenty of other gases in the atmosphere of Earth that are maintained there, that are put out there by life. So if you detect on another planet those gases that show that life is there, you can start actually talking about life, like real signatures of life around other stars. And I think this is more promising than actually looking for radio signatures. I think this is the, in like 10 to 15 years, we'll be able to start saying if there's life or not on other planets by looking in their atmospheres. And the really big mission that's coming online by NASA is the James Webb Space Telescope, which is going to be the next big mission after Hubble. You all must have seen like Hubble's amazing images, and I'm going to show a few in the later slides. But this telescope is going to be able to actually pinpoint down to one, I think to 1 in 1,000 for the closest the closest stars and their planets if there's life on them, just from measuring the composition, well, like what their atmospheres are made out of. So to answer your question, we're seeing mostly gas planets, but I think this will change in the near future by facilities like this. And yeah, like those things are coming online, like they'll be online in like a few years, and they'll be working for the next like 15 to 20 to 30 years. So like one day you could be working with them as well. Like usually those things last there for like 20 to 30 years. So nowadays students in school are going to be able to work with them. So yeah, you can dream big and really accomplish this with those things. But actually, what we also study as astrophysicists, and I'm going to jump like on a little bit higher level just to be able to show the breadth of what we're doing nowadays, is we also study these big clumps of stars, because stars in the galaxies, they're not by themselves. They're either found in those globular clusters. They're clumps of very old stars that were formed like 10 billion years ago when the galaxy was formed, and they look like this. And there's like I think about like a few 100,000 to 1 million stars all staying together, and we still don't understand how they form or why they're there, but they are there. They are there, and it's very interesting. So that's one thing we study. But also, we are studying these smaller clusters of stars. There's like 10 to 15, and those are like the birthplaces of stars. We believe that all stars start from those small associations of stars. They're like a pack of stars that start together. And what you're seeing here is the Pleiades. That's like a star cluster you can see with your bare eye in the constellation of Taurus in the evening. Actually, right now, if you go out right after sunset and you look toward the west, you're gonna see it's right above the horizon. It looks like the Subaru brand stars. Actually, Subaru means the Pleiades, so it's the other way around. But that's how you can identify it on the sky. And those open clusters are the birthplace of the sun as well. And you see all of those, all of this blue haze around those stars that I'm showing here. That's actually the gas that's left out from the gas cloud that those stars were made. And I think that's a good segue to also mention one of my favorite things in astrophysics is the study of life of stars, because part of my research is in that as well. Is that saying that since stars are found throughout everywhere in the universe, we really need to understand how they live and how they die to understand how the universe came to where it is. So just a few words about it. Nowadays we believe that all stars start from a ginormous gas cloud. It's like huge. It's like 100 times bigger than the solar atmosphere. It's very, very large. And what happens in it is that actually the gas falls on itself, and it falls on itself up to the point that it becomes so hot and dense that it creates a star. And depending on how massive star comes out of the gas cloud, as showing in this graphic here, if it's a sun-like star or like a dwarf type of star, because the sun is a dwarf star, it's not very large. If it's a sun-like star, it takes it like billions of years to live its long and peaceful life until it becomes a red giant, and then puffs up and creates a planetary nebula. And after the planetary nebula is created, usually in the center of it, there's like a small white remnant called a white dwarf that I'm going to talk about in a second. The other path you can take if you're a more massive star is that you create like a giant star, which is usually of the color, usually a white or a bluish color for our eye, because it's significantly hotter. And these massive stars, they actually live only a few tens of millions to 100 million years, which is like 100 to 1,000 times less than how much the sun lives for. And after they burn all of their fuel and they're about to, and after they're done with their burning their fuel, they actually explode in the most violent explosions we see in the universe, on so-called supernovae. These supernovae are as bright as 10 billion other stars. So you can imagine that like this one star creates like 10 billion times more light for a very short period of time. It's like, it's a glorious way to live, right? And depending on how big the star was, it either creates a black hole or a neutron star, but I'm not going to delve too much into what those things are. Maybe I'm going to talk about the black holes in a minute. But actually, astronomers for very long periods of time were trying to understand what those planetary nebulas are that they talked about previously. And I think that's the planetary nebula called the cat's eye, because it looks like a cat's eye. But actually, that's what happens when a red giant, the red giant, which is a phase of the sun's ultimate fate, when the red giant actually, it expels most of its outer layers. You can think of stars as onions. They have a lot of different layers in them. And what the red giants do is they expel the outer layers out. And you can see them here. And you can see them in these very beautiful colors, just because in the center actually is the white dwarf. This is the core of the red giant that actually illuminates them, and we see the reflected light from them. And astronomers for very long periods of time didn't understand if those are planets or not. And they were thinking that they might be comets or some other stuff. But only recently we've been able to identify them as the dying remnants of stars. And that's another one. And I think this one is really cool, because in the center of it, you can see this white dot. Can you see my cursor? No? Okay, then let me try this. Okay, so I hope you can see now. Actually, in the center over here, what you're seeing is the white dwarf that I'm talking about. It wasn't very clear in the previous one, but over here you can actually see the white dwarf remnant, which I think is super cool, because we can see all of the stages of stellar evolution and understand that. And that's been a topic of study in astrophysics for a very long time, for almost like 150 years now. And we're finally starting to get closure on all of those questions and start asking new ones. So, now I'm coming back to my black hole image. This is the black hole image that I showed in the beginning. So when a very, very massive star dies, it creates a black hole after the supernova explosion. But actually, those black holes that are being created by very massive stars, when they explode, they have a mass about the mass of the sun, so about 2 masses of the sun. They're not very large. Whereas this black hole is in the center of a galaxy, and it has a mass of about 1 million times more, to 10 million times more. So we don't fully understand how those things happen, but here we are. We have a picture of it, and I think it agrees really well with our theory, how those black holes are there. So we don't fully understand how it's made, but it's there, and that's another thing astrophysics is studying. And actually, just a few words how we were able to make this picture. It's pretty wild. So you can think of radio telescopes as you can see smaller and smaller detail if you have bigger and bigger dish. So if you build a very big dish, you're gonna see very small detail. And if you want to see this black hole here, you actually have to have a dish on the size of Earth. So what people, like some very smart people, figured out is that if you actually observe with radio dishes all over the globe, you combine the signals, you combine the radio signals in a smart way, you can actually obtain an image, you can get an image as if your telescope had the size of Earth. And that's how they got this image. Oh, sorry. That's how they got this image. It's pretty wild. And that's the first time it was achieved was a few years ago. So it's called the Event Horizon Telescope. And over here, you can see this graphic of all the different observatories that took part of it. And this is just the start. This is just the future of it. we hope to observe a lot more other phenomena throughout the universe with this telescope on a planetary scale. So I think that's something that's really, really cool that astrophysics is studying right now. And another thing that came online a few years ago as well, the LIGO, is the so-called gravitational wave astronomy. You can think of it as when two massive objects are going around each other, they actually emit waves in the gravitational field, or you can think of it as how strong gravity is pulling you. So you can actually measure these gravity waves with very precise lasers that were built by the LIGO collaboration. It stands for the very Large Interferometric Gravitational Observatory, I think. And they were able for the first time a few years ago to actually detect an imprint of two small black holes merging together. And we believe that this is a stepping stone in making one of those big black holes that I showed you before. And that's a revolution in our understanding of the universe, because you can think how we observe the universe with telescopes that look at light. Well, this is another domain. Like this is another, you can think of it as another dimension on top of light. So that's also super, super exciting. And I think it's just picking up. So it would be really interesting to see where this takes us in the future. As we can see with this type of measurements really, really far away. So yeah, that's also like something super exciting that astrophysics is doing nowadays. Okay, but and as I mentioned before, each galaxy has a black hole in its center. This is one of the largest galaxies that are close to our Milky Way. It's called the Andromeda Galaxy. And you can see it with your bare eye in the Andromeda constellation. It seems like a smudge on the sky. It's not very, you're never gonna see it that nice because this is with the Hubble Space Telescope. But you can still see it. And it's actually 2.5 million light years away. It's really, really far away. And what you're seeing here is a picture of it, how it looked like 2.5 million years ago. So that's a little bit like archaeology, as I said earlier. We see how objects look like a very long time ago. And actually, we're on a crash course with this galaxy. The Milky Way and Andromeda are gonna crash, I think, in a few million years, or like a billion years from now. So what's going to happen then is going to be pretty interesting, but I'm not gonna delve into those things for now, but we can talk about it later. But the most important thing is that galaxies are the building blocks of the universe. Like wherever we look, in what direction we look of the universe, there's galaxies everywhere. So we really need to understand how galaxies are made, how do they interact with each other, and how are they going to evolve in the future to understand how the universe is going to evolve in the future. And you can also look on even bigger scales, like what galaxies are creating in the universe. And they're creating those massive clusters of hundreds to thousands of galaxies, which create this like really large scale network in the universe. So astrophysics is also trying to understand why are those galaxies clumping like this, and if there's more missing components of the universe than we can see with our eyes, the so-called dark energy and dark matter. So that's also an active area of research that we're trying to understand better. And there's a lot of questions that are being unanswered right now. And the biggest one is why it seems like almost 95% of the content of the universe we're not being able to see it with our eyes, which is very, very strange. And it might mean that our physical theories of the universe are wrong, or that there might be, there's definitely something inaccurate in our physical understanding of the universe, and we're trying to figure out why. So that's a very essential touching point with physics and nuclear and particle physics in particular. So astrophysics collaborates with those fields very tightly. So yeah, in conclusion, I would say that astrophysics is the science of studying everything on the sky that you can see during a dark night. And I do think we're living in the golden age of space exploration. So I think it hasn't been a better time to go into this type of science and research, as more and more funds are going to be allocated for space exploration. So I think a career in either science or aerospace engineering is going to be very fulfilling in the future years. And I would love to take your questions. And if you have any other further questions, please email me on the email down here. Thank you. And I hope there's any questions now.
I do. I have one. I always have one. This is like one of my favorite topics. But you talked about light, the speed of light and light traveling, but I'm not that versed in astrophysics and that type of all this that kind of stuff. But I wanted to find out, what about darkness? Does it travel as well?
Yeah, yes, that's a very good question. Yes. So, well, if you define darkness as the lack of light there, it travels with exactly the same speed as light. Yes. So if something becomes dark, like some object stops emitting light, the darkness that comes from it is gonna travel with the speed of light as well. Yes, correct.
Thank you.
So you mentioned the two galaxies colliding. Can you explain what you believe will happen?
So we believe that they're going to crash by measuring the velocities of the two galaxies. So we can measure at what direction is the Andromeda Galaxy going toward. What's the velocity? What's the velocity and direction of its going? So we think our two galaxies are going to get really close to each other, and they're going to basically rip each other apart. Like all of those nice spiral arms you're seeing, they're going to get ripped apart. And actually, the galaxies are going to become like we believe they're going to become like massive elliptical galaxies. And the elliptical galaxies actually look like just the central part of this picture of Andromeda. So they're just going to become like large clumps of stars, is what we think is going to end. They're just going to merge into one big pile of stars with no notable spiral arms like this galaxy has right now. So yeah.
So I understand that the galaxies, even when they merge, that they're so vast that all of the planets and stars within them will still be intact, because they'll just kind of fit like a puzzle more than cancel one out. Is that correct?
That's absolutely correct. Yes, absolutely correct. Yes, actually, most of what you're seeing is empty space. Like most of the space is empty. Like out there, there's nothing. Like if you point a random direction in the sky, you're not gonna hit anything. And that's actually that's a very good point. So if you have two galaxies that actually merge, you're gonna get like one or two stars that actually merge with other stars, because it's really hard actually to merge stars. It's pretty hard due to angular momentum. But yeah, but it's just actually that's a very good point that you're bringing up, Adrian, because if the universe was endless, then the sky would have been infinitely bright in any direction. We weren't going to have a dark sky, just because in any direction there was going to be a star that you can see. So this is a proof that the universe has a finite age, like that the age of the universe is a number. It's not infinity. Like the universe hasn't been there forever, and it's not infinitely big. So that's a very good point you made.
Will our sun have died by the time the two galaxies collide?
I don't think so. I think it's going to be a red giant by that point, but I don't think it's gonna have disappeared, because actually our sun, when stars become either white dwarfs, neutron stars, or black holes, they actually those objects stay around for a while. We believe that white dwarfs, they just stay there for a while as white dwarfs until they cool down, and they cool down on it takes them to cool down and become a black dwarf on the order of I think 15 to 20 billion years. So it takes them like a really long period of time. So they're gonna be there for a while. If it's yeah, and neutron stars and black holes are also, they're most probably staying there for a while as well. Like there's some theories that black holes actually evaporate, but that's I think that's more science fiction right now actual science proved with backed with facts. Yeah, so I think the sun will be still there, but it's gonna be so long from now that I wouldn't worry about it too much. Yeah.
I got a question, and I'm kind of wondering, like, how do scientists calculate the mass, like, of a supermassive black hole?
That's a really good question. So we can't just put them on a scale, right? Like, sadly, astrophysics is one of those sciences where we can only do like remote observation. So what we know, though, from Newton's law of gravity is that stars orbit massive objects faster. So if you see a star that's orbiting around something with a certain speed, you can say that how big is the mass of the central object that's being orbited. So that's how we do it for some of the black holes. For example, the one at the center of the Milky Way, we can see the stars going around them, going around this black hole, and measure their orbit. And from this orbit, we can say what the mass is. For other black holes in other stars, we can't see singular stars going around. So we can make we can use other indirect measurements. For example, how bright is the black hole? Because of, how bright is the black hole depends on how much gas falls into it. And this depends on the mass of the black hole. So we have a lot of different ways of doing it, and some of them are more direct than others. And some of them are, and the more direct ones are better since they're more accurate. But there's a few different ways, yes.
Oh, thank you.
I want to ask about the asteroid belt. And the asteroids, you mentioned asteroids and meteors. Do they all come from the asteroid belt?
Oh, that's a very good question. I did omit a part of the solar system. Actually, there's a cloud of debris, or like there's a cloud of more asteroids and comets outside the Oort cloud. And the Oort cloud, which is significantly bigger. It's like way farther out of this picture. So we believe that some asteroids and some comets come from this far away place, but that's like something like 10,000 times farther than the orbit of Earth. It's like really, really far out. And we actually believe that this is the primordial, this is the reservoir of material that's left from when the solar system was forming. And in order to get something to fall from there, we believe that actually stars that are passing by our solar system are nudging those rocks with their gravity and pushing them in. So yeah, we've seen a few of those things fall down. And recently they passed by I think they were called Uma, and was the first object that looked like a cigar. And a lot of people were trying to say that it's a interstellar alien ship or something, which it might be, it might not be. And then there was the Ivanov object, which 2P Ivanov, I think it was a comet. It literally fell down from really far away based on its orbit. And both those objects are the very rare ones that come from this cloud that surrounds the solar system. But that's really far away, and it's very hard to observe those things. Yeah.
So the Oort cloud is like way in colder space, right? So wouldn't it be more icy material than would it heat up as it gets closer?
Absolutely correct. Yes. Yeah. So when you see a comet falling from that far, it melts as it gets closer to the sun, as it goes hotter, and it starts melting, and it creates this trail of gas and dust behind the comet tail that you actually can see them in here. They're a little bit out of proportion. They're not that long, but it's the artist's impression. But yes, you're right. Once those rocks start falling down closer to the sun, they start heating up, melting, and creating this tail of debris behind them.
Thank you. Any more questions? Oh, okay, go ahead.
Sorry, I have a question. So you said that there was that sometimes the supernova turns into a black hole, and then how in the middle of a galaxy or something like that, there's like a black hole. So how big are like both of those types of black holes compared to each other?
That's a really good question. So, sorry, I wasn't able to hear the end of it. You're asking how they compare in size?
Yeah.
Yeah. Okay. So the mass of a black hole, I think the smallest black holes that we've seen are about the mass of the sun. So they're still pretty large black holes, but they're like kind of small by galactic standards. The ones in the center of galaxies, those are like millions to tens of millions of the mass of the sun. So they're really, really large. And we don't really understand how these small black holes that form after the supernovae get to be so big as the ones in the center of galaxies. That's a very good question, and I don't think there's a good answer to that right now. Like, do they all merge together and make those large black holes? Maybe. If you're asking me about the actual size of a black hole, like the linear size, like how long they are, I don't know on top of my head, but I can come back with a number. I really don't know that right now. I'm gonna lie. Yeah.
Any more questions? You gave us a lot of information for an hour, right?
I tried to give just a more I just try to give you more breadth than depth, just because if you're interested, you can find all of those things on the internet. It's just that it's I just thought I was going to share with you like a lot of the things that we're doing right now.
Yes, yeah. And I love to go back to the topics, the projects that you're working on. Are you working on any of the mission to Mars or the Psyche? You mentioned that. Are you working on that project?
No, actually, my partner, she's working on the Psyche mission. That's why I mentioned that one.
Oh wow!
On that one, yeah. I'm working on on this telescope here. I'm grounded. I'm on the ground. That's what I'm working on.
Oh, that's good. Where's that telescope again?
In Hawaii.
Oh, okay.
Yeah, but I don't get to go there. I just
wow, that was my next question. Too bad.
Yeah. Well, hopefully after the pandemic is over, we'll be able to travel a bit more freely. Yeah. But because of COVID restrictions, we're not allowed to go up there right now. Like, because since I'm not essential for the actual construction, I'm not. I'm on a day-to-day basis. I do a lot of coding and like I work on the computer a lot. It's what.
And that's more of a solar telescope that you work on?
Yes, correct.
Okay.
Correct. It's mostly just to observe the sun, but we can also look at the stars during the night, but that's not its primary goal. So actually, this exact telescope, it's not allowed to observe during the night because it's on a native land, and the lease of the telescope doesn't allow it to operate during the night. So we're not allowed to use this telescope during the night.
Oh, wow.
As it is right now. Yeah.
So you're just hoping nothing good happens, nothing phenomenal happens with the sun in the nighttime, right?
Well, there is one in the Canary Islands as well, looking at the sun as well. So we have like one on each side of Earth. So there's always one looking up.
Oh wow, okay.
Yeah, and actually we have like this one is a pretty large telescope. It's like a 4-meter telescope, but we do have a smaller one that's I think like 15 centimeter, and we have like 6 of them around the globe. So there's always continuously one looking at them, and that's more like it's not that much research as much as operations. We are just monitoring the sun and providing space weather agencies and the meteorological agencies with continuous information, but it's more operational, whereas this is more like fundamental research based intended telescope.
Perfect. All right, any other questions for Momchil before he leaves us today? We just love to listen to, I told him, I said, hey, I want to hear about astrophysics the next time you come back. So, and I really appreciated you taking your time out. I know you have a busy day, and we will have you back. And we always would have you on rotation about every 6 or 7 months, right? I think I lost him.